Hello friends, in my last video we discussed about IEEE standard formatting for binary floating points, right? Floating point representations using IEEE standard formatting. We have seen both 32 bits as well as 64 bits. In today's video we'll discuss about some arithmetic operations such as addition, subtraction, multiplication as well as division. Again, we'll see all these arithmetic operations on floating points only, and also we'll see the final result in IEEE standard formatting, how to convert the final result after performing the arithmetic operations, how to represent the final result in IEEE standard formatting. We will see in this video. Let's start from some arithmetic operations such as addition, subtraction, multiplication and division using IEEE standard formatting for floating points. Fine, basically we'll see the arithmetic operation of floating points in today's video. So let's start the video. Floating point arithmetic. So first of all we'll see the addition of floating point binary number. We'll discuss all these things with the help of some examples so that it will be easy for you. Anyways, this topic is very easy. This is not so difficult thing. If you understood IEEE standard formatting, then this topic is very simple for you. Fine. So we have taken one example. A equals to 96.625 and B equals to 12.125. I have to add these two numbers and the final result should be represented in IEEE standard formatting, 32 bits. So what is the first step? The first step is to convert or to represent this 96.625 into binary as well as 12.125 to binary. Now in the last video we have already seen how to convert a floating point to corresponding binary numbers, right? We have already seen those things. So just convert 96.625 and 12.125 to binary numbers. So first of all we will see for 96.625. If you convert it, you will get 110000.101. This left hand side 5 times 0 is nothing but 96 and this 101 is nothing but 625.625. Fine, we already know in the last video we have already discussed. Now what next? Once we have the representation, binary representation for the floating point 96.625, next we have to make it one dot mantissa. Fine, we already know that in IEEE standard formatting we have to make one dot mantissa. So make it one dot mantissa. If you make it so, how many times you have to shift left side this dot point? 1 2 3 4 5 6. Yeah, 6 times you have to move left hand side. So the result will be 1.100000101 into 2 to the power 6. Why 6? Because 6 times I am moving left hand side. If it is right hand side, then it will be negative. We have already seen in the last video. Similarly, you convert 12.125 to binary representation. What you will get? 12.125 is nothing but 1100.001. Now how it is 1100.001? To know all these things, please see my previous video. Now once I have the binary representation, this one also I have to make it one dot mantissa. So make it, if I make it one dot mantissa, it will be 1.100001 into 2 to the power 3 because 3 times I have to move left. So this is what we get. Now here is the next important thing we have to remember. These two steps are very easy. Third step is I have to check out of these two numbers which number has the highest mantissa or the largest mantissa. Sorry, largest exponent, not mantissa. If you see, this A is having exponent as 6 and B is having exponent as 3. So this one is the largest one, 6 is the largest one. So what we have to do is we have to make this 3 also to 6. I mean, for both the numbers, exponent of 2 should be always same and the exponent should be with the largest number. We cannot make it 3. We have to make it 6. You understood that, right? Because 6 is the largest one, well, I will make it 6. Fine. So once I make this to 6, what I have to do? Check it. If I want to make it positive, then what I have to do? I have to move left hand side, right? How many times? 3 more times I have to move left hand side. So if I do so, how it will look like? See, this is the original number 1.100001 and all other zeros we have. Fine. If I move it to left hand side, 3 times left hand side, then how it will look like? It will look like 0.001 100 whatever I have, right? 3 times I am moving left hand side, so that this 2 to the power 3 will become 2 to the power 6. The aim is to make this exponent same, and we will go with the largest value. Fine. Now we have 2 to the power 6 in both the numbers. First number is 1 dot this and second number is 0 dot this. Next is we will just add these two numbers just like our normal binary addition. How to do that? Whatever Mantissa part we have, 1.100 this part and second number is 0.00 this one. For both the numbers 2 to the power 6 is the exponent, right? Now you just add these two numbers just like your binary number. 0 plus 0 is 0, 0 plus 0 is 0. So this is nothing but a normal binary addition now. Is that clear? What we are doing? Again I am repeating. Okay, I have one more example, so I will explain once again. So once I get the result, what next? Now I have to represent this number into IEEE standard formatting, 32 bits, right? For that we know the rule. So here in this number, if you ask you what is the sign bit will be positive, so it is 0, we know that. What is my exponent? E dash here. E dash is E plus 127. What is E in this example? 6. So E dash will be 6 plus 127 equals to 133. So 133 is E dash, 0 is sign bit, and Mantissa is 10110011 and all zeros. Fine, we have to fill 23 bits for Mantissa. So if we understood that, then the final result will be something like this. 0 is the sign bit, this is nothing but 33, and this is the Mantissa 101100 and all. I hope you understood this. I have one more example. So the next example is add 0.25 with 100. A is 0.25, B is 100. What is the first step? Convert A, whatever A I have, to binary representation. Do it. 0.25. If you convert it back to binary, it will look like 0.0100 because I don't have anything in integer part, right? So this is the number I got after converting back to binary. Next, what I have to do? I have to make it 1 dot something. So if I want to make it 1 dot something, now I have to move right side, not left hand side. In the previous example, we moved to the left. Now we have to move to the right. So it will be 1.00, right? So 1.00 into 2 to the power minus 2 now because I am moving 2 times right hand side. Similarly for 100, convert it back. If I convert 100 to binary representation, it will be 1100.0 because this side I don't have anything. This one also I have to make 1 dot something. So to make it 1 dot something, I have to move left for this, right? How many times? 6 times. 1, 2, 3, 4, 5, 6. So it will be 1.1001000 into 2 to the power 6. Fine, you understood that? What next I have to do? I have to make this exponent same for both the numbers, and we will go for the largest one. What is the largest value I have out of these two? 6. That means somewhere I have to make it 6. Fine. What is there? I have minus 2. From minus 2 I have to make it 6. So how many times I have to move? 8 times, right? 8 times left hand side. So check it how to do that. This is the original number I have, 1.00. I have to move 8 times left hand side. So it will be what? 0.7 times zeros, 100. You understood that? Why it is like that? So once I have both the numbers, so first number is this one, 1.100100, and second number is this one. Now I am ready to add the numbers. So do it. Next part is very easy now. Just add these two numbers. Just binary addition. This is nothing new. Now sometimes after addition, here you may get 1 1 or 1 0 dot something. It's always not you will get 1 dot something after addition. After addition because of some carry out bit you may get 1 1 also. If you get so, then you have to make it 1 dot. You know that, right? 1 dot Mantissa. Now what is the exponent E dash here? Here also E dash is nothing but 6 plus 127, right? Why 6? Because for both the numbers 6 is the highest exponent which we considered. So here E dash will be 133, and then sign bit will be 0, and Mantissa is 100, whatever I have here. So this is how we add two numbers in IEEE standard formatting. I hope you understood that. So if you understood this one addition, then we'll go for subtraction. So before we go for the IEEE standard subtraction, let me ask you, can you remember the normal binary subtraction? If no, then please have a revision here. Please have a quick look and please pay attention. I know many of the students already they cannot remember it, they already forgot it. So how to do the normal binary subtraction? This is the first number 1100010101, and this is the second number 100101101. If I ask you to subtract this to this, how to do that? Just listen carefully. What I will do? 1 minus 1 is 0. You have to remember that. 1 minus 1 is always 0. And 1 minus 0 is 1. After this is fine. Now how to subtract 0 to 1? I cannot do 0 minus 1, right? I cannot subtract it. In that case, what I will do? I will borrow immediate 1 from the left hand side. If I have immediate left, fine, otherwise I will search wherever I have. So here I got 1. Now please note a point. Once you get a 1, this is not 1. Now this is 1 0. Please make a note. Once you get a 1, this is 1 0 now. You cannot consider only 1. It's not 1 minus 1. It's 1 0 minus 1. So what is 1 0? 1 0 is 2, right? We know that 0 0 is 1. Sorry, 0 0 is 0, 0 1 is 1, and 1 0 is 2. So 2 minus 1 is 1. You understood that? So once I have borrowed 1 to this place, here I have 0 now. This place is 0 now. Now I cannot subtract 0 to 1. This is not possible. So what I have to do, again I have to borrow 1. So from where I will get, I will check the immediate left. I don't have. Here also I don't have. Here also I don't have. Yeah, here I got 1. So what I will do, I will borrow this 1 to this place. Why? Because this 1 was borrowed by some other person. That's why it's 0 now. Understood that? Now once this 1 is borrowed to this place, this is becoming 1 0, not 1. It's just similar with this case. So this is 1 0. 1 0 is 2. So 2 minus 1 is 1. You understood that? Now one more point you have to remember here. Whenever I am borrowing 1 from any place to any other place, if in between if I get any zeros, if on the way if I get any zeros, I have to make all the zeros 1. This is becoming 1, this is also 1, this is also 1. You understood that? If I am going through some zeros, these zeros will automatically become 1. So this 1 0 minus 1 is 1. This is 1 now. I told you why this is 1, right? 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 0 is 1. Here I have 0. So 0 minus 0 is 0. 1 minus 1 is 0. So this is how we do the normal binary subtraction. I hope you can recall it now. So if you understood that, we are ready to go for the arithmetic operation or the subtraction operation in IEEE standard formatting. So we'll go with the same example. What is the example? 96.625 minus 12.125. How to do it and how to represent in IEEE standard formatting. So first you convert A to binary. We know how to convert it and make it 1 dot something. So we made it 1 dot something. Similarly for B also convert it to binary. Fine, and make it 1 dot something. Then next again you have to go for the highest exponent. Same with addition. The first few steps are exactly same with the addition. So here also we'll go with the highest exponent, which is 6. So to make it 6, I have to move left hand side, and finally my B will become something like this. I hope I should not explain all these things again, because you already have gone through in addition, right? Same steps, there is nothing new here. So once you have these two numbers, now you are ready to subtract. So subtract it. This is the first number, this is the second number. In the previous case we added, and here we will subtract. And how to subtract? I have already shown you how to subtract two binary numbers in a normal way. 0 minus 0 is 0, 0 minus 0 is 0, like this we are subtracting. So after subtraction, what I got? 1 dot this much. Now represent it back to IEEE standard formatting. You can easily do, right? What is the sign bit here? 0, because positive number. What is exponent dash or E dash here? E dash is 6 plus 127, which is 133, and main part is there. Just place it. Fine. One more example we will see, which is 100 minus 0.25. Same thing, you just convert this 100 to binary number and then represent it in 1 dot something into 2 to the power something. Similarly for B also you do the same thing. Next, you have to go for the highest exponent, which is 6. I have to make 6 here also. To make it 6, it's minus 2. So if you want to make it 6, I have to move 8 times left hand side, right? Then only it will become 2 to the power 6. If I move 8 times, then it will be minus 2 plus 6. So it will be, sorry, minus 2 plus 8. So it will be minus plus 6. And then if you have both the numbers, then you know what to do, right? What to do? Just subtract it using the normal or traditional subtraction method. So just subtract it. 0 minus 0 is 0, like this. So here you see 0 minus 1 is not possible, so I am borrowing this 1. So it's becoming 1 0. 1 0 is 2, right? 1 0 minus 1 is 1. And these all zeros are filled with 1. I told you why. Because you are moving this 1 from this place to this place. So all these zeros will become 1. So this is also 1, this is also 1, this is also 1. This is 0. So like this we are doing the subtraction. After the subtraction, just represent it back to IEEE standard formatting, right? 0 is the sign bit, 133, why? 127 plus 6 again, and this is the mantissa. Fine, I hope you understood. Next we will go for multiplication. If you understood addition and subtraction, we will go for multiplication. Multiplication is the easiest arithmetic, I will say. If you compare with addition and subtraction, multiplication is the easiest one. So before I jump for the multiplication for floating point, I want to ask you a simple question. Can you recall how to multiply two binary numbers in a traditional way or normal way? Can you remember that? If not, let me just quickly revise it, how to do binary multiplication in a normal way. So which is very simple and as almost as it is like we do in decimal numbers. Same thing. Say I want to multiply 9 into 6 in binary. So this is 9 in binary, this is 6 in binary. So how to do the multiplication? Bitwise same like our decimal number only. First, I will multiply all these bits with rightmost bit of second number. Next, I will multiply all these bits with the second rightmost bit of this number, then this, then this. Fine? Means 1 into 0 is 0, 0 into 0 is 0, 0 into 0 is 0, 1 into 0 is 0. Then I will just move left. I will just move left by one bit. Then I will start multiplying with this bit. 1 into 1 is 1, 0 into 1 is 0, 0 1 is 0, 1 is 1. I will move one bit left. Then I will multiply with this one. 1 into 1 is 1, 0 1 is 0, 0 1 is 0, 1 1 is 1. So one more bit I am moving, and finally 1 0 is 0, 0 0 is 0, 0 0 is 0, 1 0 is 0. Then you just add all these bits, normal binary addition. What I am getting? This one. If you convert it back to decimal number, you will get 54, and 9 into 6 is 54. So this is the correct result. This is how we do the traditional binary multiplication, right? So let's see how to do in floating point number multiplication. Before we go for binary, just I have one example of decimal multiplication. If I have two numbers, 3.5 into 10 square and 5.25 into 10 to the power 4, and if I ask you to multiply these two numbers, forget about binary, how you will do that? So normally people will do, they will multiply 3.5 and 5.25 and then 10 square and 10 to the power 4. We know 10 square and 10 to the power 4 is nothing but 10 to the power 6, right? 8 to the power m into 8 to the power n equals to 8 to the power m plus n. Then you will multiply this and 10 to the power 6 you will get. This is the traditional way we do, right, for decimal number. Same thing we will do for binary number also. How? So this is the binary number I have given to you. Multiply this number, these two numbers. Here also we will do the same thing. What? We will take 2 to the power 3 and 2 to the power 6 this side, and 1.11 and 1.010 on this side. And these two will multiply using traditional multiplication techniques, which I have already shown you in the first multiplication slide. So after multiplying these two, you will get this, and here you will get 2 to the power 9. Now this is not in IEEE standard format, right? You have to make it in IEEE standard formatting. So to make it, what I have to do, I have to make 1 dot mantissa, not 1 0 dot. So if I make 1 dot mantissa, then it will be 1 dot 0 0 1 0 0 1 1 into 2 to the power 10, because I have to move it left side, right? Then what is the exponent dash? If I know that, then what will be the exponent? Yeah, what will be the exponent dash here? 10 plus 127, which is 137. What is my mantissa? This is the mantissa. What is the sign bit? 0, because this is positive. I hope you understood. So this is the final binary arithmetic representation in IEEE standard formatting. I hope this is clear for you. So if you understood multiplication, now we'll go for the division. So division is again So there are some rules, multiplication rules, whatever I said, those things are there only, nothing else. You can take a screenshot and you can note it. Now we'll go for the division. If you understood addition, subtraction and multiplication, division is nothing very difficult. It's almost same. It's almost like our normal decimal division only. I'll discuss this division with the help of one example. It will be so easy for you and very clear for you. So what is the example I am taking? Say I want to divide this one 91.34375, this is in decimal, by 0.1445312. This is my dividend and this is my divisor. If this is the question you got, first thing you have to convert it back to binary. So 91.34375, if you convert it back to binary, you will get something like this, 1011011.01011. So once you get this one, you have to make it 1 dot something. If you want to make it 1 dot something, it will be what? 1.01101101011. So how many times you have to move it left hand side? 1, 2, 3, 4, 5, 6 times. So it will be 1 dot something into 2 to the power 6. I hope you understood that. Similarly, for 0 point this, if you convert it back to binary, it will be 0.001000101. But you have to make it 1 dot something. If you want to make it 1 dot something, it will be what? 1.00101 into 2 to the power minus 3. Why? I have to move 3 times right hand side, right? So this is the number you are getting. So once you have these two numbers, this and this, I won't suggest you to immediately make it in IEEE standard format. You can skip it as of now. As of now, I have this and this. Now simply I have to divide this number with this. What to do with 2 to the power? See, in addition, what we did, we took a common exponent of 2 and we made it same for all. Subtraction also we did the same thing. In multiplication, what we did, we added the exponent, right? For the first number, if it is a, and for the second number, if it is b, if it is 2 to the power a into 2 to the power b, we did 2 to the power a plus b. For division, we know a to the power m divided by a to the power n equals to what? A to the power m minus n. That means the final exponent will be 2 to the power something minus whatever they are in divisor minus whatever they are in dividend. So it will be 2 to the power 6 minus 2 to the power 6 minus of minus 3. So it will be 2 to the power 6 plus 3. Ultimately it will be 2 to the power 9. Right? So 9 will be my exponent. So that part is clear. Now I have to divide this part with this. So how to do that? This is almost similar with our traditional division technique only. See here. So this is the divisor, this is the divisor, this is the dividend. Fine. So what I have to do is, how many bits I have here? 1, 2, 3, 4, 5, 6. So here also I have to take 6 bits. 1, 2, 3, 4, 5, 6. So these are the 6 bits. This side also I have, this side also I have 6 bits. Now if I divide these 6 bits with the first 6 bits here, it may be either 0 or 1, but after that I will have dot because it's 1 dot, right? Either it will be 0 dot or 1 dot. So forget about dot now. Just take it 100101 and here I have 101101. Is it possible to divide? Yes, this is bigger. This side I have bigger numbers in this 6 bits. So it will be 1 dot. If it is smaller, then it will be 0 dot. Fine. So I can divide it as 1 dot. Fine. So 1 dot. If it is 1 dot, then what I will do? That means this 6 digits is possible to divide by this. Forget about dot now. I have written dot here. Just assume that there is no dot only. So 1 times I can divide this 6 bits. So if I can divide in 1 times, then what I will do? What do we do in traditional division? We multiply this with this, right? So same thing we will do. So 1 into these 6 bits will be 1 into 1 is 1, 1 into 0 is 0, then 1 into 1 is 1, 1 into 0 is 0, 1 into 0 is 0, and 1 into 1 is 1. Then you subtract it, just like our decimal division only. If you subtract, what you will get? 1 minus 1 is 0, 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 0 is 0. So I have how many bits here? 1, 2, 3, 4. And you know, after subtraction, I can take the next bit from the main dividend back here, right? So this one I can take it down. Still I have how many bits? 1, 2, 3, 4, 5. Here how many bits I have? 1, 2, 3, 4, 5, 6. Means this is not possible to divide. I need one more bit. Now I cannot simply take this 0 down. I know that. right? In decimal also we cannot simply take it down. In decimal what we do? We put 1 0, right? After that I can put the next one. 1 is free. First one I can easily take, but second one if you want to take, I have to put 1 0 in decimal. Same thing here. I want to put one more bit. Why I want one more bit? Because this is not possible to divide now. This is smaller. That's why I need one more bit. To take one more bit, I have to put 1 0 here. This 0 is given because I want one more bit. So if I put this 0, I can take next 0 also here. So 1, 2, 3, 4, 5, 6. Now I have 6 bits. Here also I have 6 bits. Now you check this 1 0 0 1 0 1, and here I have 1 0 0 0 1 0. Is it possible to divide? Still, though I have 6 bits here also, but this is smaller than this. If you check it, if it is smaller, you cannot divide. Then what you have to do? You have to take one more bit from top. So for that I have to put one more 0 here. If you put one more 0, this one I can take it down. Now I have 7 bits. Now I know easily I can divide, right? So now I can divide it 1 times. So if I divide it and it goes 1 times, just multiply it again. So it will be 1 0 0 1 0 1 1 0 0 1 0 1. Then subtract it. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 1 is 0. 0 minus 0 is 0. 0. And 1 0 minus 1 is 1 here. This is 1. Remember, this is not 0. 0 minus 1 is not possible. So I am borrowing 1. 1 0 1 is 1 here. So next what? Next, after that, this 1 I can easily, this 0 I can easily take it down. After subtraction, 1 is free, right? One bit I can easily take. Now what I have? 1 0 0 0 0 0 0. Yeah, this is the number I have. Now is it possible to divide? Yes, this is bigger. So one time I can. So if I divide it 1 times, then what I will get? 1 0 0 1 0 1 again. Now subtract it. Now 0 minus 1 is not possible. I have to borrow 1. So from where I will get? If you see here also 0 0 0 0 0 1. From here only I will get. So this 1 will come here and it will become 1 0. So 1 0 minus 1 is 1. And this all zeros will be filled with 1 as we know. So 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. And this side you have 0. And take this 1 back here. Now check it whether I can divide this to this or not. Yes, this is bigger. So 1 times I can. If so, then I will get again 1 0 0 1 0 1. Just subtract it. You will get 1 0 0 1 0. And if you take it 1, then it will be 1 0 0 1 0 1. Exactly 1 time I can divide. You understood? So what is the final result? The final result is this 1.001111. If that is the final result, what is my exponent? My exponent is 9, right? Exponent is 9, but E dash will be what? 9 plus 127, which is 136. So finally my representation will be something like this. 0 I am putting in sign bit because this is positive. 136, this is nothing but 136 I am putting in E dash. We know why. And these all are Mantissa. What is my Mantissa? 0 0 1 1 1 1 0 0 1 1 1. Rest all the bits I have to put zeros, as we know from the previous class, previous lectures. So this is how we do arithmetic division when we talk about IEEE standard formatting. So that's it for the session. I hope you enjoyed the video. If so, then please do subscribe the channel.